Hello, good morning everyone. Once again, welcome to the world of electronics. Our lesson for today is the last part of the switch mode power supply. And this is all about the voltage regulation system, in which the DC output voltages here are stabilized and held constant despite of the variation of the input. So here it goes, class. To verify the condition of the circuits and the voltages, we will be using three digital multimeters here and a variac transformer. Variac transformer is an electrical equipment that will vary the voltage from the outlet. So here it goes, class. As you rotate this rotor shaft counterclockwise, the voltage is lowered to almost 0 volt AC volt. Then the maximum actually here can be set to 268 volts. So this is now the operation of the variac transformer. Variable AC transformer. Variac transformer. So we will use this one to verify the condition of the voltages and the circuit, of course. So we are using here three digital multimeters, wherein the first digital multimeter is connected to the outlet of this variac transformer that provides 222.2 volts. That is now the AC volts being supplied to this switch mode power supply. Okay, we are now connecting the switch mode power supply. Actually, this is a switch mode power supply of a DVD player, wherein the AC cord is connected now to the outlet that receives 220 volts, 222 volts, AC volts. Then the second digital multimeter is actually connected across this capacitor here. The voltage across this capacitor actually is an unregulated voltage being rectified by this rectifier diodes and smoothed out by this capacitor here. So we have here this capacitor. Okay, we know already that the voltage that is stored here will reach up to the peak value. So we can speak of a higher voltage here. Then the last multimeter is connected across this capacitor. It is a DC output voltage, and it is expected that the voltage here is regulated 5 volts. So we're using now here the multimeter, which is set to DC voltmeter, and it is actually connected here. That is across this capacitor. Okay, so the voltage of the outlet now, which is supplied to this switch mode power supply circuit, is around, we will set that one to 220 volts from the outlet being distributed by the electric company like Soleco, Leyeco. Then the voltage across this capacitor is around 299.4 volts. You might be amazed how come it reached to 299 volts or 300 volts. Because this capacitor stores the voltage up to the peak value. However, the voltage at the output being regulated by the voltage regulation system or circuit is now 5 volts. As it is indicated here, it's 5 volts or 5.02 volts. Okay. If we will lower down the voltage here at the outlet, we will set this one to, for example, the voltage lowered down to 186 volts, because there are times wherein the voltage at the outlet being distributed by the Soleco company will rise and fall. So let us consider, or let us assume that the voltage here is 195 volts. Then the voltage across this capacitor lowers down to 266.0 volt. You can notice that the voltage are varying. No, for every now and then. The voltage across the capacitor is 265.5, 265.4. It varies for every now and then. It is in accordance with the variation of the voltage at the outlet here. However, the voltage at the output, which is a regulated voltage, retains the same. There is no variation actually. It is always constant, 5.02 volts, as it is indicated here. But if we will try to increase the voltage from 200 to 120 varies to, let us say, 235 volts or 233 volts at the outlet, the voltage across the capacitor now increases to 318 volts. But the voltage across the output here retains the same, despite of the variation at the input. See? Lower down the voltage here, but the voltage at the output retains the same. Increasing the voltage here, retains the same. That is how the voltage at the output is stabilized and regulated by the voltage regulation system. If we will lower down the voltage here to 100 volts or 90 volts, retains the same, because a switch mode power supply is an auto volt power supply wherein it can be supplied 90 volts, still the output provides 5 volts, because all electronic appliances today are auto volts, as what is indicated here. We have here this unit DVD player can be supplied 9 volts up to 250 volts. Meaning to say, although it is 90 volts, but still the output voltage here retains the same. Because all electronic appliances today are actually auto volt. Because other countries, the voltages there at their outlet are actually 100 volts. So, these units can be applied to anywhere around the world. For example, of this TV receiver, the TV receiver of the Devant LED TV, it is 43 inches, wherein at the back panel, you can read the specification that this TV unit is supplied with 100 volts up to 240 volts with a frequency of 50 to 60 hertz. Okay? Actually, here in the Philippines, the frequency of our AC volts is 60 hertz. If we try to measure the frequency here, it is actually 60 hertz. That is 60 hertz. We set the range selector switch to hertz, to the frequency meter that measures the frequency, 60 hertz. So, the voltage in the Philippines, all the electric company like Soleco, Leyeco, Bico, and other electric companies are actually distributing 220 volts up to 240 volts. However, our electronic appliances will accept that voltage up to 240. Then, if you are using 100 volts, still the unit will operate. Then, the voltage at the output retains the same, 5.02 volts at the circuit here. Also, if we will measure the voltage here, it is also 14 volts because there are two output voltages here, the 5 volts and the 14 volts. Okay. Now, it is now made possible by the voltage regulation system. The three important circuits that play important role in the regulation of the voltage at the output is made possible by these three important circuits. We have here the precision shunt regulator, then the optocoupler, and the voltage controller. These are the three important circuits that play important role in stabilizing and regulating the voltages at the output. So, we have actually here it looks like a bipolar transistor or a field effect transistor. We have here actually the precision shunt regulator. But this is not transistor. It is actually IC, integrated circuit, because it has 3 electrodes. It has 3 electrodes. We have here the actual spare parts. It is TL431. It is not a transistor. This is now the reference, the first, then the anode, and the cathode. We have here the actual electrode configuration. TL431, 1, 2, 3. The first terminal is reference. The second at the center is anode. And the last is the cathode. And we have here the symbol actually. Then the internal circuit. But if we are going to search the internal circuit of this TL431, it goes like this. This is actually the actual internal circuit of this component, IC. This is not a transistor, but this is IC, TL431. This is now actually the internal circuit. It is integrated circuit because it is the combination of 2 or more electronic components. There are many transistors and resistors, and we have also capacitors. And we have actually here the output, the cathode, the anode, and the reference correspond to the 3 electrodes here of this spare part. So, actually the measurement is different from the bipolar junction transistor. We will come to that later on. Okay? So, why is it that this TL431 is called shunt? It is precision shunt regulator because it provides precise voltage by sending feedback signal to the optocoupler that will dictate the operation of this voltage controller IC. Then, it is precision. Then, why it is called shunt? Because the output voltage here that provides 5 volts DC is just across the shunt regulator. Because the other regulator that we have was a series regulator. It is a series regulator. Okay? It goes like this. Okay. The regulator that we have last time was all about linear mode power supply, which is using, it goes like this class. We have here the Zener diode here, connected to the ground here, chassis ground. And we have here the resistors. Okay. Actually, this transistor is a regulator, which is in series with this output line here. So we call this one a series regulator. However, this precision shunt regulator, it is called shunt in the sense that the output loads are actually across this shunt, the precision shunt regulator here. We have here. Okay. Okay. The voltage regulation is actually done to the other circuit. There is no series transistor here that will reduce the voltage across. So, the output load here, which is 5 volts, is just across this precision shunt regulator. It is parallel. The other term for shunt is parallel. Unlike the other one, the previous one, that was the series regulator, wherein the collector emitter is in series with these 2 resistors. Okay. So, it goes like this class. The reference is actually connected here. that has two resistors in parallel or in series. Okay? We have here now the output line, 5 volts. Then the two resistors are here, connected to the chassis. When we talk of chassis, this one class, chassis ground. When we talk of the earth ground, that is connected to the earth, using the power line here. Okay. We have here the 8 kilo ohms and 8 kilo ohms. So, 5 volts. Each of the resistors will drop 2.5 volts. Another resistor here will drop 2.5 volts. The sum of the voltage drops of these two resistors is actually equal to the 5 volts output. Okay? So, it is now connected to the reference here. We have here the shunt regulator. Okay? It is actually a Zener diode in symbol. So, but it has 3 terminals. This is not simply a Zener diode, but it is IC. So, we can expect of 2.5 volts here. That will be fed to the reference. The reference here, from this reference terminal to the anode or to the ground, is 2.5 volts. So, it is considered that the voltage is regulated, retains 5 volts. So 2.5 and 2.5 here. But there are times that the voltage increases. Let us assume that the voltage increases from the outlet. From 220 increases to 228 volts, for example. So, let us assume that the voltage here increases to, let us say, 6 volts. Or 6 volts. It increases to 6 volts because there is an increase at the outlet. From 220 increases to 230, for example. So this is now 3 volts and 3 volts. If the output voltage here is 6 volts, so the voltage drops across the two resistors are 3 volts and 3 volts. So here, the reference voltage now of this precision shunt regulator is 2.5. Then, the voltage here being sensed or detected by the sense circuit of this precision shunt regulator is 3 volts. There is an increase of 0.5. So, that will be compared by the comparator here. Actually, we have here. There is a comparator here of this circuit here. It is compared. And there is error. There is an increase of 0.5 actually. Because 2.5, then the voltage here is 3 volts. There is an increase 5 volts, 0.5 volts. So that since voltage here is compared and amplified. Because there is also an error amplifier here that will amplify the error being detected by the sense circuit here. So, that will be submitted to the optocoupler or to the voltage controller here via optocoupler. It is via optocoupler. So, this diode now is a light emitting diode that receives the feedback signal because there is a change of voltage here. The voltage actually increases to 6 volts. Then, the voltage at this point is 3 volts, which is over the reference voltage here, which is 2.5 only. From this reference terminal to the ground, 2.5 reference. But the detected or sensed voltage from the output here is 0.5 volts. There was an increase of 0.5 volts because 3 volts and 3 volts. 3 volts and 3 volts. So 6 volts. So, we can expect of 0.5 volts difference between the 2.5 here and the 3 volts. So, that is detected after being compared and amplify that error and submit it to the voltage controller via optocoupler. So, what is this optocoupler class? So, we have here the optocoupler. This is now the optocoupler. It has 4 terminals. It has 4 terminals. It is IC actually because it has 2 components, a diode and a phototransistor. Okay, so what is this light emitting diode actually we have here? This is actually the actual optocoupler. There are 4 names of this optocoupler actually class. Aside from optocoupler, it is also an opto-isolator because it isolates the 2 opposite circuits, the cold side and the hot side or the hot circuit. That's why it is also called as opto-isolator. Then photo-isolator or photocoupler. It has 4 names actually. So, why? Because optocoupler is a semiconductor device that transfers the electrical signal here, the feedback signal being provided by this precision shunt regulator. It is transferred to the other circuit using light. They are not actually physically connected. Okay? So let us prove. We have here, if we are going to measure or to verify that there is lead here, it goes like this class. So we will set this one to times 10 ohm range of this analog multimeter. Let us measure if there is internal diode there, here. Okay? The positive side here of the ohm meter actually is connected to the anode here. We have here the anode. No? Okay. Okay, it goes like this class. We have here the symbol, actually the internal circuit of this optocoupler. Okay. Pin number 1 here. So, we can identify that this is pin number 1 because there is dot here. There is dot at this point. Dot. And we have a notch. So, we need to say that this is number 1, this is number 2, this is number 3, and this is number 4. So, if you are going to connect this one here, the pointer deflects. So, we need to say this is now the anode and this is now the cathode. If we will reverse, there is no deflection of pointer because it is reverse bias for the light emitting diode. Also, at the secondary or the opposite side is the 2 terminals of the phototransistor. A phototransistor actually class is an active component which is sensitive to light. When this light emitting diode emits light, so this transistor will be activated. So there is no deflection pointer. There is no actually deflection pointer here. Reverse and opposite polarity. So that is the normal measurement of this optocoupler. Because if it is defective optocoupler, it goes like this class. It is actually forward bias for this diode inside, but there is no deflection. Even you reverse the polarity, there is no deflection. But it is at the other side, it is normal. There is no deflection here because infinity between emitter and collector once there is no light being submitted to this phototransistor. So this is open or defective optocoupler class. Defective optocoupler because there is no deflection. It is open. You can no longer use this one. This was actually destroyed by the application of higher voltage. The maximum voltage that can be applied here is only 1 volt, 1.1 or 0.9 something volts. No? But if the application of voltage here is higher than 1 volt, so there's a probability that this IC will be ruined or destroyed. No? Okay. So, it goes like this class. So, we will connect. We have here the positive side. And the negative side is over here. Okay. We will connect this one to a certain voltage here. This is now the negative side. and the positive side is over here. Then we will measure the voltage across this one here. If really this transistor turns on, so set this one to 1K. If there is deflection here, set it to 1K, 1K. We have here 1K. Okay. It turns on actually. Turns on. This negative side is actually connected to the emitter, to this terminal here. Emitter number 3. And the positive side is connected to the collector here of this optocoupler. So, there is deflection. But once this is disconnected, there is no applied voltage to the light emitting diode here. So, there is no deflection. So, this phototransistor conducts if the LED is supplied with voltage and it gives light. This transistor is a phototransistor which can be energized by the light submitted by the LED. Actually, the LED here is sometimes infrared LED. Infrared LED. Infra LED. Meaning to say that although the voltage here is forward bias, let us, for example, let us apply this with voltage using, okay, where was that voltage? Okay, we will use again times 1 ohm range to measure the two types of light emitting diodes here. So this light emitting diode, once it is supplied with voltage from the ohmmeter, it gives light. Light emitting diodes will convert the electrical energy here from this battery to electromagnetic radiation into light at visible range. We have here. So, internally, actually, this optocoupler uses sometimes LED that emits light at visible range. But if in case it is an infrared LED, it deflects the pointer, but you can't see any light because the light is invisible. That's why it is called infra, meaning below. Harder or the redder is the visible range. So, below the visible range, there is light emitted, but it is beyond the visibility of the human eyes. But with the use of cellular phone, you can see the flickering light. For example, of your remote control. Okay? There are two types of LED being used by the optocoupler. Most often times, it is an infrared LED, wherein the phototransistor is sensitive to that infrared or infrared light. No? Okay. So, there are actually two light emitting diodes being utilized by the optocoupler. So, again, optocoupler here is a semiconductor device that transfers electrical signal here to the opposite side of the circuit by means of light. So, what is being transferred here is the feedback signal. The sense change of voltage here, because there was a change of voltage here being detected by this precision shunt regulator being compared to the reference 2.5 volts here. Then there's a difference. So that error 0.5 difference will be amplified before it is submitted to this optocoupler. This diode actually will drop 1 volt. Okay? So what is being dropped here? And the current also here is varied. It is varied from 100 milliampere to 150 milliamperes. That depends upon the feedback. Sometimes the voltage here negative or positive. Let us say it becomes let us say 4 volts at the output. So meaning to say 2 volts and 2 volts. That makes it 4 volts. So, 2 volts, then the reference here is 2.5. There's a difference again. Negative 4 or negative 0.5. Diba? Because 2 volts, then this is 2.5 volts. Reference voltage is much bigger. So, negative feedback that will be sensed by this sensor here, then submit it to the control voltage IC through optocoupler. Okay. It goes like this, class. Okay. Try to observe this one here. There are 2 coils actually here. There are 2 coils. Primary and secondary coils, which are not physically connected. But, okay, we have here. Observe the light here. Okay. Once it is put closer to the primary here, it gives light. See? Although they are not physically connected, because the voltage here, the magnetic field transfer or cut across to the secondary coil here by means of electromagnetic radiation. There is a mutual inductance here. This secondary coil induces voltage derived from the variation of the voltage here. Okay? This is actually the principle of the radio transmission and reception system. No? The radio transmission and reception system. We will consider this one as the cell site. In every municipality, there is always a cell site that you're always looking. You must be getting closer to that cell site in such a way that your cellular phone can get not only 1 bar, 2 bars, 3 bars, 4 bars. If there is 5 bars, 5 bars. If there is a very strong signal. But if you are far from the cell site, the signal there is 1 bar only, then it is very hard for you to use your cellular phone because it is only 1 bar. Especially 0 bar. You are very far from the cell site. That is the principle of the radio transmission and reception system. So, the signal here, the voltage here is transferred to the coil without physical connection. It is transferred by means of the magnetic field. Okay? Okay, it goes like that, class. That is to verify that the optocoupler, the phototransistor, and the light emitting diode here are not physically connected. So, the signal here, and the electrical signal, transferred to the other circuit by means of light. Once it emits light, the LED, the phototransistor, which is sensitive to light, that's why it is called photo, which is light, will be activated. No? Okay. It goes like that, class. Okay. Let us now come to the voltage controller IC. What is that voltage controller IC, class? So, actually, as what you have learned before, okay, that there is actually a switching transistor here. It is actually a MOSFET, metal oxide semiconductor Philippine transistor, that turns on and off the voltage here. There is a 325 volts here across this capacitor, which is submitted or supplied to the primary winding of the switch mode transformer. Is switch on, switch off, switch on, switch off by means of the switching resistor. It is actually mandated by the clock pulse generator, diba? As what we have demonstrated last time, it goes like this. Okay. It goes like that. So, positive, negative. Negative here. Okay. Okay, there was error again. But that was the flickering of the pulses. It pulses. When it gives light, it is like this here. When it pulls down, off. On, off, on, off. Okay, it goes like this, class. These are now the pulses. We've heard the actual pulses outputted by this pulse generator. no? On, off, on, off, on, off. Which will mandate the operation of the switching transistor. Because the switching transistor is supplied with voltage from this pulse. Okay? It goes like this. So, we have here a transistor. 1, 2, 3. Connected to the earth here. This one connected to the coil, the drain. We have here the drain, the source, and the gate. The coil here actually is supplied with 225 volts. Okay? Which will be turned on and off by the switching transistor as mandated by the pulses over here. We can consider this one as the clock pulse generator that is fed to the gate of the switching transistor. When it is turned on, the transistor will conduct. So there is a flow of current here from source to drain. But anytime that it is dropped to zero here, cut off. There is no flowing of current here. Zero. So that should be the action of the switching transistor. On, turn off, turn on, turn off, turn on. In such a way that there is variation of the magnetic field here that provides voltage at the output. Is still AC. Okay? So it goes like that, class. So there is usually voltage outputted by this clock pulse generator. So it goes like this. If we are going to measure the voltage here using AC voltmeter, we will use AC voltmeter. Okay? Negative is here. Negative is here. Then the output is here. See? See? So, the voltage actually is varying. On, off, on, off, on, off, on. Every time that it lights, there is voltage. But anytime that it drops to zero, meaning to say that there is no light. So that would be the voltage which is fed to the gate. So the switching transistor actually is being triggered by the clock pulse signal fed to the gate. Okay? So it goes like that, class. Okay. So how many times that the clock pulse, that the transistor turns on and off, that depends upon the frequency being generated by the clock pulse generator. So, because the high frequency circuit here uses frequency ranging from 20 kHz up to 1 MHz, let us assume that the frequency being generated by this clock pulse generator here, it is located internally of this IC, is 100 kHz. It is 100 kHz, meaning to say that the transistor turns on and off 100,000 times in 1 second, because there are 100,000 pulses, 100,000 pulses in 1 second. So, how many pulses in 1 second here? Probably it has 3 pulses only, 3 hertz in 1 second. But if we will increase the pulses, so probably there is 10 pulses in 1 second or 10 hertz only. But the clock pulse generator here, which is located internally of this IC, can reach up to 1 megahertz or 1 million pulses in 1 second. So let us presume that the number of pulses here is around 100,000 pulses or 100,000 kilohertz, 100 kilohertz. So that is generated by the clock pulse generator here. So the transistor turns on and off 100,000 times in 1 second. However, these pulses, the width, we call this one as the pulse width. No? The pulse width. Pulse width. Okay? The pulse width is actually the time that the transistor is conducting. At this point, the transistor is conducting. But at this point, the transistor is cut off. So actually, this switch mode power supply is sometimes called as PWM. Thus, switch mode power supply. It is PWM or pulse width modulated. It goes like this, class. Okay, this is now the period. One cycle. Period is the time it takes to complete the on and off state of the cycle. This is one cycle or 1 hertz. So, when we talk of pulse width, that is the width of the pulse that the transistor is conducting. Okay, because if the voltage here reduces from 5 volts, reduces to 4 volts, so 2 volts and 2 volts here, then the 2 volt is being compared to the reference, which is 2.5 volts. So there is a difference. The circuit is not working very well. So that will be submitted to the voltage controller via optocoupler. So there's a need of dictating the switch resistor here to work harder. So the pulse width will be increased here, just like that. So the width, this is one cycle actually. The duty cycle or the pulse wherein the transistor is conducting is the duty cycle. Duty cycle is the ratio of the pulse width to the pulse period. The period actually is the complete cycle, no? For the on state and the off state. But the width of the pulse width or the duty cycle, that is now the operation of the transistor which is working, is increased. This is 50%, 50%. 50% on or 50% conducting the transistor, 50% off or resting the transistor. It goes like this, class. 50% on, off, the same time for on and off. But if there's a need of increasing the operation of the transistor here because there is a decrease of voltage at the output from 5 to 4, so 2 volts here being compared to the reference of this precision shunt regulator, which is 2.5, there's a difference of negative 0.5. So that will be feed back to the control IC. So the pulse width now or the duty cycle of the transistor is increased. So from 50% it is increased to 80%. It is increased to 80%. So there's a need of doubling the operation of the transistor before it is cut off. So that increases the voltage again here. Both the two outputs are actually controlled by the pulse width. It is now the pulse width. But if in case the voltage increases to 6 volts from 5 volts, so 3 volts, 3 volts, 3 volts is actually higher than the precision from the reference voltage 2.5. So there's an increase. So that will be submitted to the controller here. So there's a need of reducing the operation of the transistor here. So instead of 80%, 20% for the rest, so we will make it 20% duty cycle or turning on the transistor and 80% for the rest. So the transistor should rest or off 80% because there was an increase of voltage at the output. So the pulse width now wherein the operation of the transistor is only 20%. So pahinaan natin ang operation ng transistor because there's an increase at the output. So that reduces the operation of the transistor. So actually, it is only the pulse width is being adjusted. But the frequency retains the same. 100 kilohertz. 100 kilohertz is retained. So that is now the frequency here. But the pulse width is modulated. Actually, pulse width is modulated, or the other term is varied by the feedback signal. So it is now the feedback signal which is transmitted via optocoupler that will vary the pulse width here. Vary the pulse width. Okay? So, what is the time actually? So, it goes like this, class.